Hi, this is Dr. Goldstein, and today I'll be talking about how we find global extrema. So our conversation begins with the extreme value theorem that we've looked at before, which says that if f is a continuous function on a closed interval a, b, then there are x values, capital M and lowercase m, such that f of capital M is the maximum y value and f of lowercase m is the minimum y value. So to paraphrase this a little bit, the idea is that a function f has a global max and min on a closed interval. And paraphrasing a little bit less, we know that f needs to be continuous. You can't have any breaks, jumps, or skips in it. So what this theorem doesn't tell us is how exactly to find these max and min values, and so that is what we are going to look at today. To get us started on this, let's look at a couple of examples. So in the picture on the farthest left, we have a continuous function on a closed interval from a to b, and we can look at the picture and see that at this point here, I have a maximum value, and at this point here, I have a minimum value. So this x value a corresponds to this little m, where I have the minimum y value f of little m, and this x value here, big M, corresponds to where I have the maximum y value, f of big M. Now in the second picture, we can see that the maximum occurs at B and that the minimum occurs at A. In the third picture, we can see that the minimum value is right here, is at this point, and the maximum value is again at B, is again right there, and in the last picture, our maximum value is right there, and our minimum value is right there. And again, what we say is that these values occur at the x-coordinate, but the actual value is the y-coordinate. So the way that we say this is that I have a global max of whatever the y value is, so of y equals f of big M at x equals big M, and I have a global minimum of y equals f of little m at x equals little m. So what we can see from these pictures is that in the case of a continuous function on a closed interval, that our global max and min occurs at either a local max or min, so necessarily at a critical point, or at an endpoint. So the idea is that we want to check critical points and endpoints to determine whether they are the global min or max. We want to check critical points and endpoints. So let's see how this works in a couple examples where we don't have a graph in front of us. So let's look at the function f of x equals x squared minus x minus 6, and we are going to look on the closed interval from 0 to 4. So I will just say at the output, we can expect to find a global min or a max because this is a continuous function. And our interval is closed. So the extreme value theorem tells us we have a global max and min. We know that already. Okay, so like we just said, we need to find critical points. So in order to find critical points, I need the first derivative. And the derivative in this case is f prime of x equals 2x minus 1. I need to check where that's equal to 0, so I have 2x equals 1, so x is 1/2, and that is my critical point. And so now we check, we compare the y values at critical points and endpoints. And this is literally just a take those x values and I plug them into my function f of x. So I have x values and I have f of x, which in this case is x squared minus x minus 6. So I know that I have to check x equals 1/2. That's my critical point. And I need to check the value 0 and the value 4. So again, I have one critical point and I have two endpoints. And I'm checking their values. Okay, if I take 0 and I plug it into f, I have 0 squared minus 0 minus 6, and so this gives me 6. If I plug in 1/2, I have 1/2 squared minus 1/2 minus 6, and this you can use a calculator for if you like, but this is going to give me negative 6.25. If I plug in 4, so I have 4 squared minus 4 minus 6, so that's 16 minus 4 minus 6. This is going to give me a value of 6. Oops, I'm sorry. When I plug in 0, I get negative 6. That was silly of me. I lost my negative sign. So I can look at these values, and again, these are just y values. These are y values. And I look at them, and I say, okay, the biggest one that I have here is y equals 6. This is the biggest. And so this is my max. And so the smallest value that I have is negative 6.25. This is the smallest. And so this is my minimum. And so overall, I have a global max of y equals 6 at x equals 4, and a global min of y equals negative 6.25 at x equals 1/2. So in this case, one of my global extrema happened at a critical point and the other one happened at an endpoint. Okay, let's look at another example. So I'm actually going to use the same function, but I'm going to look at a different interval. So in this problem, I still have f of x equals x squared minus x minus 6, but now I'm looking at the interval from -2 to 3. So we found on the previous slide, we found the critical point of x equals 1/2. And so now all we have to do is to check the y values to find the biggest and the smallest. So I like to do this in a table. It keeps my work organized. I have my x values and I have my f of x values. So I need to check my endpoints, -2 and 3, and I have my critical point, 1/2, which is between them. If I compute f of -2, so I have -2 squared minus -2, so +2 minus 6, that ends up being 0, We already found that f of 1/2 was minus 6.25, because that's the same value from the previous slide. And f of 3 is going to be 3 squared minus 3 minus 6. This also comes out to 0. So in this case, when we look at our y values, the smallest is definitely minus 6.25, so this is our minimum. But we look at the y value of 0, and that's the biggest y value, and it occurs in 2 different places. So both of these are our global maximum. This is perfectly fine. And so the way that we have this, the way that we write this, is that we have a global max of y equals 0, but it happens at 2 different x values. So x equals minus 2 and 3, and we have a global min of y equals negative 6.25 at x equals 1/2. So we have a min and a max. The maximum happens to occur at more than one place, but it's just the one value. So that is another variation that happens sometimes in these problems. Okay, let's move beyond the scope of the extreme value theorem now. What if the interval that we're working with is not closed, or the function f is discontinuous on the interval? So in this case, the extreme value theorem does not apply, and we are not guaranteed to have a global max or min. We might have them anyway, but we might be missing one or both of them. So let's look at the same function that we've been dealing with. So this is f of x equals x squared minus x minus 6. And in this case, we're going to look on the interval from 0 to 5. And notice that this interval does not include 5. This is what we call an open endpoint. If you were to graph the function on this interval, you would have an open circle at x equals 5. So again, this is the same function that we found before, that we looked at before, and we already found that the critical point is at x equals 1/2. But one thing that we can notice for this particular example is that it's not in the interval. And since it's not in the interval that we're looking at, we can ignore it. Maybe there's something going on at x equals 1/2, but I'm not looking at x equals 1/2. I'm only looking between x equals 1 and x equals 5, not including x equals 5. I'm only looking between there. Okay, so here, again, I want to check my endpoints, and I actually don't have any critical points to include on this interval. I have 1 and I have 5, but remember, this value 5 is not included. So if I plug 1 into my function, I have 1 squared minus 1 minus 6, and that comes out to negative 6. And if I plug 5 in, I have 5 squared minus 5 minus 6, and that comes out to 14. So I do still have a maximum value of 14, but it's not included because this point is not included on my interval. I do have a minimum value of minus 6, and this point is included on my interval. So for this problem, I have a global min of y equals minus 6 at x equals 1, but I have no global maximum. If I wanted to graph this function quickly just to show you visually what's going on is I know that my function is going up from 1 to 5. So here's x equals 1, x equals 5. My function is increasing, and I do have this minimum value here. That's obviously not y equals -6, but so my picture is not drawn to scale. But at x equals 5, I have this maximum value, but it's not included. It's an open dot. And so we do not actually have a global maximum on this open interval because I'm missing that endpoint. So again, if your interval is not closed, you might be missing a global min or a max, and this is one of the ways in which that can happen. Let's look at one more situation. So let's say that we are looking at the function f of x equals 1 over x minus 1 on the interval from 0 to 2. So in this case, we notice that this function is discontinuous at x equals 1. This function is not defined at x equals 1. So again, the extreme value theorem doesn't apply because our function is not continuous on our interval. So we may be missing a min or a max, or we may not be. Let's find out. So we want to start by taking the derivative of this function. And in order to do that, I'm actually going to rewrite f of x as x minus 1 to the -1. And so then when I compute the derivative of f, I can use the chain rule. I take down the -1, and my exponent becomes -2. And then the derivative of that inside x minus 1 is just 1. And so simplifying this, we get -1 over x minus 1 squared. So I could have used the chain rule, but this is actually quicker in this instance. And so I look at this derivative and I say, okay, this derivative does not exist when x is equal to 1. And this is actually not a critical point because it's not in the domain of the function. This derivative is never equal to 0. So there are no critical points. So again, I technically do not include x equals 1 as a critical point because this is not in the domain of f. So when we look at this function, we do want to check the endpoints, and we also do want to check this point of discontinuity because something funny might be happening there. And in particular, if you think about what the function is going to do there, if you take the limit as x goes to 1 of this function, you get infinity, maybe positive, maybe negative. So we look at x, we look at f of x, which is 1 over x minus 1. And in this case, I want to look at my endpoints, 0 and 2, and I also want to look at the limit as x goes to 1 of my function. I can't look at x equals 1. I can't actually plug that into my function. It's not defined, but I can look at the limit as x goes to 1. So when I plug in x equals 0, I get 1 over 0 minus 1, which simplifies to -1. When I plug in 2, I get 1 over 2 minus 1, which is just 1 over 1, which is 1. And it turns out that when I take the limit as x goes to 1, well, let's do this a little bit off to the side. The limit as x goes to 1 of 1 over x minus 1, when I actually evaluate this, it is 1 over 0. And so I split up into left and right limits. So I take the limit as x goes to 1 from below, and the limit as x goes to 1 from above. From the left, I end up with 1 divided by a very small negative number, so I get negative infinity. And from the right, I get 1 over a very small positive number, so I get positive infinity. And so comparing x values back in my table, the limit as x goes to 1, I get minus infinity and positive infinity. So visually what that looks like is at x equals 1, here's 1, I have a vertical asymptote, and to the left my function goes down, and to the right my function goes up. That's what that looks like. So the fact that my function gets infinitely large and infinitely small, gets infinitely large in both the positive and the negative direction, so it means that I have no global min or max since the function grows infinitely big, both positively and negatively. So this function, that infinite discontinuity at x equals 1, means that I'm not going to get a global min or max for this function on this interval. Okay, so let's summarize everything that we've seen. We want to compare the following values in order to find the largest and the smallest values of the function. We want to compute f of c for any critical points. You plug it into the function, you figure out what the y value is. You also want to take any closed endpoints and plug those into the function. And in both of these cases, you will actually use that minimum or a maximum that you find. In the third case, we want to calculate f of c, or the limit as x goes to c, for any open endpoint or any non-domain point. And in this last case, we can't actually use these values, because either they are not included in our interval or the function is not defined. So this is because they are not included or not defined. So again, like I said about 1 and 2, these will actually give us usable maxes and mins. And part 3, we can't actually use those values because they're not included or they're not defined. But as we saw in the last example, I'll flip back to that for a second, x equals 0, I have y equals 1. This is not a min. This is not the global min. Because the function gets smaller than that. Because the function goes to negative infinity. And this down here at x equals 2, I have the y value of 1. This is not a global max because the function goes to positive infinity. So again, I do have to check the values in part 3. I do have to check any open endpoints or non-domain points, but I can't actually use those as my max and mins. They might disqualify other maxes or mins because I figure out that my function actually gets bigger or smaller, but I can't actually use those. So, summary, critical points, endpoints, non-domain points. That is what you have to check to find global maxes and mins.